So we're from Group 7 Section 1 and we'll be analyzing PQ problem and mitigation technique for lightning impulse, voltage sag and harmonic distortion. In modern electrical system, there's many sensitive devices and nonlinear loads that are used. So this leads to common power quality problems such as impulse transients, voltage sags, and harmonic distortion. So this disturbance can cause equipment failure, reduce efficiency, and increase maintenance costs. So for our project, the objective is to simulate each of these issues using MATLAB, analyze their effects, and apply suitable mitigation methods to solve them. So our focus in this project is to improve system performance and ensure a stable and reliable power supply.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Izhan bin Mawad Shahan and my metric number is DE220147. Now I will explain about the literature review of our project where we choose 3 cases in the power quality issue. So the first one is impulse transient. What is the impulse transient? Impulse transient is a sudden or short duration spike in voltage or current that occurs in the power system, typically caused by the external factors like the lightning strikes or internal events such as a switching operation or equipment faults. This transient can damage the sensitive equipment if not mitigated. As you can see the figure in this slide, there is a spike in the voltage waveform at the normal AC voltage. And the second case that we choose, which is the voltage sag. Voltage sag is a temporary reduction in voltage level in the power supply, lasting from a few milliseconds into several seconds. It is often caused by the short circuit, high starting currents of large motors, or high heavy electrical loads, and can disrupt and the operation of the voltage sensitive device. As you can see the figure in the slide, the voltage sag happen at the 0.03 second until 0.06 seconds. And last but not least is the harmonic distortion. So basically, harmonic distortion is a power quality issue where a nonlinear load introduce the additional frequency into the electrical system, distorting the ideal sinusoidal waveform. This can lead to reduce the efficiency, overheating of equipment, and also increase the wear on electrical infrastructure. As you can see the figure in the slide, where the additional frequency occurs in the waveform, which is third harmonic, fifth harmonic, and seventh harmonic, and the result as shown in the figure, which is at the line current on the color yellow. So that's all from me. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fadlan Hazim Fazila and my metric number is DE220105. I will present to you our methodology project. Okay, this is our flowchart. Okay, to begin our project, we first identified 3 major power qualities disturbance, which is impulse transient, voltage sags, and harmonic distortion. These were selected because they are commonly encountered in both residential and industrial electrical system and can severely affect the performance of lifespan of electrical equipment. Next, we conduct a theoretical review to understand each disturbance root cause, impact, and relevant mitigation strategies based on IEEE and IEC standards. This step helped from the foundation for the design for our simulation models. Following the literature review, we produce with MATLAB simulation for each disturbance. For every case, we run 3 simulation scenarios, which is first, pre-disturbance, steady state, second, during disturbance, and for the last one, post-mitigation. Each simulated circuit was analyzed by measuring waveform quality, voltage levels, and total harmonic distortion where relevant. All results when compiled into a comprehensive project report and into a poster to present our findings visually and clearly. Finally, the complete methodology flows ensure a structure, repeatable process, which is from problems identification through simulation to solution evaluation, enable practical understanding and insight into real-world PQ issues. Thank you.
Right, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faizal Hadi bin Zulkifli. So today I want to present for the case 1 for the first problem, power quality problem, which is lightning impulse. Still here we got the model in simulate model. So now we want to simulate the so we have to simulate this we have to simulate before the power quality problem, which is lightning impulse. So now we're gonna run, and then we see the steady state waveform. So as we can see here, the waveform has no distortion, no voltage fluctuation, so all are well balanced in steady state. As we can see here, this is all in steady state in nominal value, confirming that this is a very stable system. So this is for the pre power quality problem. So now we're going to continue with the uh, during the power quality problem. So during the lightning, we just include this lightning block. So now we simulate, and then we can see, and then now we see. So as we can see here, this is a huge, very huge spike. As we can see, this we can't really see there is a sinusoidal waveform there. This is very huge, which is about 10k kilovolt spike. That's a huge spike. Is it because I have set here, which is about 10k impulse magnitude, which is represent the lightning. So that's we can see here the very huge spike there, and then we could also see here the RMS value. As we can see, the RMS value is huge, which is 3874 volts, which is compared to this cursor, which is about 221 volts. So compared to during the fog, it's about 3,874 volts. So that's for the during the problem. Alright, now we continue with post problem, which is we include the surge arrestor, which redirect the lightning current, which is going to redirect the current to the ground, which have it is function to protect the electrical equipment from overvoltage, which divert the excess energy to the ground. So now we're going to run this, and let's see the output voltage. Alright, now as we can see here, there's a small spike here, which is about just within the permissible range. As you, this is just a small spike. As I'm going to prove it with the RMS block. As we can see here, the average RMS during the fog at this small spike is about 225 volts, and compared to the RMS during steady state is 212, which is proof that it is just within the range of 120% of the voltage range. So this is considered as acceptable. So that's all for the lightning impulse. Alright, now we're going to simulate for the second problem, which is the voltage side. So for this one, we just eliminate this DVR and fog, then we just run. So this is 311 kV to 400 volts under normal operation. So as we can see here, the load voltage is all in normal steady state condition, no distortion or no voltage drop. As we can see, this is at the bus 1 and this is at the load. So that's for the pre-voltage set problem. So now we're going to continue during the fault. So as now we just include this fault here and then we run. This is, let me just review the parameters. As we can see here, the 0.04 ohms, and it is the switch is about in between. Yes, the fault is assigned in between 0.03 and 0.07 seconds. So now we're going to see the voltage waveform. So as we can see here, there is a huge voltage drop, or we can say voltage set, very visible here between the 0.03 and 0.07 seconds. As we can see, there is a huge voltage drop and distortion, which is including the decrease in amplitude due to the line to ground fault. Alright, so now we're going to continue with post voltage set, which is how to mitigate this. Is we include this DVR, which is the dynamic voltage regulator. So as we can see here, we all now we're going to run. So we want to mitigate this voltage sag. This DVR is designed to actually detect the abnormal voltage and inject a compensating voltage to maintain the steady state output. So now we're going to see the waveform. So as we can see here, before the DVR, here it is still maintain the voltage sag, which is decrease in reduction of the amplitude of the voltage, and you can see here there's distortion as well. So after the DVR, which is at the load voltage, we can see here all the it is in steady state. It is maintained because DVR injected a compensating voltage. As we can see in the V injection between the 0.03 and 0.07 seconds, the DVR injected compensating voltage to maintain a steady state output for the circuit. So that's all for voltage set.
Assalamualaikum, my name is Muhammad Faiz Farhan Haizam and my metric number is TE2200884. So now I will present about the case 3 is harmonic distortion. So we have three conditions: pre-PQ condition, steady state analysis, and the second is PQ issue during harmonic distortion, and the lastly is post-PQ condition after mitigation measures. So the first is pre-PQ condition steady state analysis. We focusing on the pre-PQ condition or the steady state scenario. Here we analysis the system under normal operation. Before any harmonics introduce, the goal is to establish a clean baseline for comparison before any power quality issue simulated. Okay, for the scope result, the power system operates with ideal sinusoidal waveform at a fundamental frequency of 50 Hz. There are no nonlinear components present in the circuit, so the current and voltage waveform are clean and undistorted. This condition reflects stable and efficient system performance with minimal electromagnetic interference. Okay, next about the THD result. As shown in the total harmonic distortion or THD results, the harmonic content in the waveform is very low. The THD value is within acceptable IEE limits, confirming that the system is operating in a healthy, undistorted state. This steady state serves as the reference point for comparison against the next two phases during and after harmonic distortion. Okay, next is PQ issue, means during harmonic distortions. In this section, we examine what happened the harmonic distortion is introduced into the system. The purpose is to simulate the common real world issue caused by nonlinear loads such as industrial rectifier or converters. We analyze the impact on waveform quality and system stability. So this is a circuit diagram for the PQ issue during harmonic distortion. Next, for the scope result, a 12-pulse thyristor control rectifier is added to the system representing a non-linear load. So this load generates significant harmonic frequencies including the 3rd, 5th, 11th and 13th harmonics, which distort the waveforms. As a result, both voltage and current waveforms becomes jugs, no longer resembling a pure sine wave. No longer resembling a pure sine wave. Okay, for the THD result, the total harmonic distortion or THD has now increased to 13.89%. This value is considerably higher than the IEE 519 recommended limits for power systems. Such distortion can lead to overheating of equipment, reduce system efficiency, poor power factor, and interference with sensitive electronics. Okay, the lastly is post-PQ condition, means after mitigation measures. So this focus on the post-PQ conditions after applying mitigation measures. This phase evaluates how effective harmonic filtering is at reducing the impact of nonlinear loads on power quality. So the goal is to restore waveform integrity and bring THD down to acceptable levels. So this is a circuit diagram for the post-PQ condition, means after mitigation measures. Okay, next for the scope result. To mitigate the harmonic distortions, three-phase passive harmonic filters are reconnected to the system. These filters are tuned to target specific harmonic orders, such as the third, 11, and 13, and help absorb or cancel them. After applying the filters, the waveform becomes smoother and more sinusoidal. Okay, lastly is the THD result. The THD value has now dropped from 13.86% to 11.52%, showing clear improvement, although still slightly above the IEE limit. This result confirms that passive filtering effectively reduces harmonics. For even better results, especially with variable loads, we recommend use active filter or low harmonic drives in future design. Okay, so next about the distortion harmonic. In summary, harmonic distortion is mainly caused by nonlinear electrical device. When left unfiltered, it severely affects waveform quality and system efficiency. After mitigation using basic harmonic filters, we observe better waveform integrity and reduced THD. For further improvement, we recommend implementing active harmonic filters or low harmonic drives, which provide more dynamic and adaptability filtering in real time. So, thank you.
So to conclude our presentation, we have successfully simulated and analyzed three major power quality issues, which is the impulse transient, voltage sag, and harmonic distortion. So each problem was tested in three stages, before, during, and after the mitigation, to see how it affects the system and how it can be improved. Surge arresters, dynamic voltage restorers, and harmonic filters were effective in solving the problems and improving the overall power quality. So this project shows that applying the right mitigation method can protect equipment, reduce losses, and improve system reliability. So that's all from our group. Thank you.